Jülich and IST Lisbon, is going to talk about mesoscale mode coupling theory for weakly driven system. Gunter, thanks for accepting the invitation, and the floor is yours.
Right. Okay. So, well, thank you for inviting me to the seminar. Now, the title you have seen, you also see my outline. Now, the first part is really, will not give anything new to you. Basically, it serves to introduce notation and the kind of setting that I want to discuss, but it will all be very familiar to you. Then I will discuss how one can treat these systems in a non-rigorous fashion using nonlinear fluctuating dynamics. I also want to give you something that comes out of this treatment, which is in section 3, the supernatural universality class. And then, only then, I will come to the new point, which is a further development on this mode coupling theory, so as to adapt it to the case of weakly driven systems. And I will explain exactly what I mean by this in the first part. Okay, and then I will end up with a short summary and some open questions that I think are interesting to tackle. Okay, so now what kind of systems am I going to talk about? I will talk specifically about the ASAP, but this will be in the context of a more general setting, namely of particle systems in one dimension with short-range interactions. Now, there are many types of such models. For instance, there are harmonic chains. Now, in these models, typically you have conservation laws like energy, momentum, and other quantities that are just conserved under the evolution of the system. So even though there's noise, we can conserve some of these quantities. Another type of model are less lattice gases like the ASAP. But the ASAP, as you know, is one kind of particle, but you can also have many kinds of particles which are individually conserved. Now, either way, whether you have these chains, harmonic chains, or lattice gas, or other models, if you have m conserved quantities, then are somehow locally defined, then there will be stationary currents that will be associated with these conserved quantities because, well, this conservation, these particles or whatever it is, can flow through the system. And in particular, if you have a driven system, you will have a flow even in the invariant measure when you are in a steady state of your system. Okay, so this is just a completely general statement. Now, which will be true in any dimension for any system, but what has been found specifically for one-dimensional systems is that you can have dynamical phenomena which are not just diffusive, but actually super diffusive. The famous KPZ, Kardar-Parisi-Zhang universality class, is an example, but there are more examples. So basically, the goal would be to try to find some kind of classification of such universality classes in terms of dynamic exponents and scaling functions. Now, what does universality mean? Well, it means that many microscopically different systems will, on sufficiently large scale, exhibit the same behavior with the same quantities that will not depend on the microscopic details of your model. And this is what one ideally would like to classify. And then, of course, once one has such a classification between different kinds of systems, of course, the question starts, well, how do you go from one to the other? Okay, so these are two general questions that one can ask about these systems. And it is in this setting where I want to make a small contribution with this talk. Okay, so let me now be a bit more specific. Let me remind you of the ASAP, which, as I say, I'm sure you all know, but just to introduce my notation. So the ASAP is an interacting particle system on a lattice. In my case, a one-dimensional lattice, can be a torus or infinite. So where each lattice side is occupied at most one particle. So there's an occupation number which can be 0 or 1, and the whole configuration will just be the set of occupation numbers. And the jumps are Markovian jumps with rates that go to the right and to the left with potentially different rates. So there is an exponential clock attached to each of these particles, and after the exponential time, they jump to the right or to the left, and the rates here in this notation are G10 to the right and G01 to the left. So you can see here, this can go to the right, to the left, this guy can go to the right, but this guy cannot go to the right because the side is occupied, so it cannot jump from here to here, because then you would have two particles on the same side, and this can't happen. For the same reason, this guy cannot jump to the left, right? This move is not allowed. Okay, so now if we are on infinite lattice or on a periodic system, we know that the translation invariant measures are Bernoulli product measures with density rho. And if these rates are different, then there will be a stationary current, which is just the difference of these rates, this bias G10 minus G01 times rho times 1 minus rho. That's this functional dependence of the current is simply a consequence of the product measure. Okay. Now, this is stationary behavior, very easy. But what is more interesting is what are the fluctuations that you see in this system. Now, fluctuations can be characterized in many, many different ways. And the way how I want to characterize them is by the dynamic structure function, which really is the covariance of this occupation number at site k times tau minus its mean minus rho, or more precisely, the Fourier transform of this. So here, this is the covariance nk of tau minus rho times n0 of 0 minus rho expectation. And here is just my definition of Fourier transform that you see here. Okay, now there are two fundamentally different cases. One is when the zero bias is zero, in which case we have the symmetric simple exclusion process. Then it's actually very easy to compute this dynamic structure function. It's if you go to large scales, that means if you take q, the momentum to zero, and time to infinity with q squared over tau fixed, then this will just be exponential of d minus q squared tau, where d is this diffusion coefficient. So this is a simple exact result, which tells you that this distribution, that this function is basically a Gaussian, and the dynamic exponent, which tells you how you have to scale space and time, is true. You see it here in the q squared. Now, if there is no, and as I say, this is a behavior that you see not only for the symmetric simple exclusion process, but for many, many systems. The diffusion coefficient, that will depend on the microscopic details of the model, but this functional dependence will always be exactly like this on these large scales. That's what universality means. And this universality class is called Edwards-Wilkinson universality class. Now, if the ASAP is non-zero, that is, if there is a drift, then it turns out that it's not diffusive anymore. The dynamic structure function is of the following form. First, here is a term which has to do with the average drift, which is not important. But here is the important part. This is a scaling function, which is a function not of q squared times tau, but a function of q to the 3 over 2 times tau. So here you see a different dynamic exponent, which is 3 over 2. This function here, this has been found. It's a very non-trivial function. It's a solution of some Pauli-Levé equation. Anyway, it is sort of, in some sense, explicit. And lambda is given in terms of microscopic parameters as square root of 2 times the second derivative of the current. Okay, so this is what is known. And this is characteristic for the so-called Kardar-Parisi-Zhang universality class, is dynamic exponent 3 over 2. So this is well-known stuff for the ASAP. Now, ASAP has one conservation law. What happens if we have more than one conservation laws? Will we also see diffusion and KPZ depending on whether it's symmetric or not, or can something different happen? Well, so let's look at this problem. Now, as I say, there are many problems with many conservation laws. I take a particularly simple system, namely, I take multi-lane ASAPs with conserved densities rho alpha. So what are these models? Well, basically, you have several ASAPs, right? In this case, in this picture, just particles jump in the simplest case just to the right, like in the totally asymmetric case. Now, if these independent ASAPs, and that's it. However, I will make these rates of jump to the nearest neighbor set depend not only on whether there's a particle or not, I will also make dependent on the occupation of the neighboring chain on this bond. So this particle here will jump to the right with the rate R1 of 0 because there are 0 particles here on the other lane. This one here will jump with the rate R1 of 1 because there's 1 particle here. If there were 2 particles, would jump with the rate R1 of 2, and so on, right? And the same for the other lane. This guy here, it jumps with rate R2 of 2 because on this box, there are 2 particles, right? This guy would jump with R2 of 0 because on that box, there is nothing, right? So you always look at the box in which the jump occurs. You look at the box on the other lane. And here are the rates. So this R1 of k is a constant B1 plus another constant times the sum of particle numbers on the other lane. And R2 of k is B2 with the same constant here, and then the number of particles again on the other lane. And this, of course, you can generalize to M lanes, to as many lanes as you wish, and also think of other interaction between the lanes. You can think of full exclusion or partial exclusion, no exclusion at all. You can define similar pros for zero range and so on. So this is but I will stay right now to be definite with this ASAP. Okay, now for this kind of model, it has been shown that the invariant measures are Bernoulli product measures with densities rho alpha. So each lane has its own density rho alpha, but otherwise it's just product. This means that the stationary currents on the lane alpha are just rho alpha times 1 minus rho alpha. This is the part that comes from the K-zip. And here is the B alpha, this constant, times gamma times rho beta, where rho beta is the density on the other lane, right? Okay, so these are the currents. Now, what can we say about fluctuations? Well, the fluctuations, again, I want to study in terms of the dynamic structure function, which is now the Fourier transform of the stationary correlations of these fluctuations here. So I take nk alpha, which is the pile number on lane alpha at side k times tau minus the mean, and I look at the covariance, and this is this C alpha beta k of tau. Okay, this is the quantity I'm interested in. Just a little remark, if I take the sum over all k, then this will not depend on time anymore because of the conservation law. It will just be the compressibility matrix, which is in this case for the product measure, rho alpha times 1 minus rho alpha times delta alpha beta. And also, if I look not at the sum of these, but if I look at the time derivative of k times the sum, then I get another time-independent quantity. This is a little bit less trivial to show, but anyway, what happens is that this quantity here is the current Jacobian. That is, you take J alpha, take the derivative with respect to rho beta, and this gives you this J alpha beta, which you can also obtain in this fashion. Okay, so these are simple things you can read off from this function without much great deal of computation, but really what we want to know is the behavior of this function for a large k and a large tau, or in the Fourier transform for small momentum q and large tau. So what we would like to know ideally is which dynamic exponent do we get and which scaling functions, right? This is the question. Now, unfortunately, for this kind of system, there is no exact answer. This has not been really studied very well, neither mathematically nor heuristically. So what can we do? Well, what we do is we apply the theory of nonlinear fluctuating dynamics to this problem. What is the idea here? Well, first of all, we look at the high dynamic limit and Eulerian scaling. This, I guess, it hasn't been done for this model, but I think it can be proved without too much difficulty, at least if there are no shocks. You can do the usual stuff. You constrain space and time, and you rescale space and time in the same fashion. So you take k is equal to x over a with tau equal to t over a with x and t fixed, and you take this lattice space in a to 0. It's like zooming in, zooming out with a video camera and play the movie faster than on microscopic scale. Then you use the usual arguments. I just give as a general reference the book by Claudio and by Kipnis. So use pile conservation, law of large numbers, and use local stationarity, and you end up with this hyperbolic system of conservation laws. As I say, it hasn't been proved, at least on generality, but I'm sure this is what will come out. Okay, so here is your Jarin Jacobian, which is a function of the densities, and they come from the stationary current density relation. So this is your... Okay, let me make a remark on this, because this is still deterministic, doesn't say much about fluctuations. Let me just look at the significance of this current Jacobian, because it tells us something important. Namely, just linearize this in this nonlinear equation. That is, you define a function u alpha of x and t as rho alpha of x and t minus stationary value, and you make an expansion to first order in this u's. Okay. Then what you get is still an equation of the same type, but now this j here, this is just a constant, doesn't depend on rho and x and t anymore, just a function of your stationary background densities. It's the current Jacobian with these values, rho alpha, valued at these rho alphas. Now, this is now a fairly simple equation, and you can see immediately that you can solve it. Namely, you can diagonalize, you see this is an equation for a vector, you can diagonalize your matrix here. That means you make a transformation of what is called normal modes with this diagonalizing matrix R, which is chosen such that it diagonalizes the current Jacobian with eigenvalue C alpha. And also, for convenience, you normalize it such that R times the compatibility matrix times R transpose is equal to 1. This is just a normalization of your modes, which is convenient to use. And then after this diagonalization, this equation here turns into that equation, which is completely decoupled. Right? So it's just a set of linear first order equations. So the solution of traveling waves phi alpha of x and t, simply phi 0 alpha of x minus c alpha t with this initial data, right? So this little exercise tells you something about the eigenvalues of the current Jacobian, namely, basically, they are the speeds of traveling waves. So imagine you start with an initial data that has just a little bump localized. This localized bump will just be carried with speed c alpha. Okay, so that's what these eigenvalues mean. Okay, now comes the more important step. Which is really nonlinear and fluctuating dynamics. So what do? Well, you take the same hydrodynamic equation, but now you expand to second order, and also you add a diffusion term and Gaussian white noise. Now this, I should say, this phenomenological, you just do it hoping kind of that it gives you a good answer. And of course, I wouldn't tell you this if it wasn't shown in many examples that is the case. Anyway, what you end up is the following. You go to your normal modes, and here you get your linear part of the evolution, right? This first term here. The second order expansion gives you a term like this. So it's basically quadratic in the fields phi alpha with some constants which come from the Hessians of your current Jacobian, from the H's, right? Then here's your diffusion term that you have added, and here's your noise that you have added. Now, diffusion term and noise are added in such a way that they satisfy in equilibrium fluctuation dissipation theorem, but otherwise you just put it in by hand. So from this, now you have a stochastic partial differential equation, and now you can study fluctuations. Let me make another comment here. I say I expand to second order. Of course, you can ask, well, why not to third order, fourth order, fifth order, and so on and so forth. Well, it has been shown already a long time ago by Spohn and de Villard that if you put higher orders, then the long-time behavior will not change. That is, if you want to study universal properties, you can ignore higher order terms. And another remark is these Burger's equations, as we all know, relate to the Kardar-Parisi-Zhang equation simply by saying that the phi alpha is the space derivative of a height function, right? So this you can also interpret as coupled KPC equations, noisy KPC equations. Okay, it's just a comment. Okay, now we have this equation here, right? This SPDE, which of course, again, we cannot solve in any explicit form. So we have to analyze it further. And here comes now what is known as mode coupling theory. Again, it goes back to old work by van Beieren, Spohn, and Kuttner. And you find a review of this in this paper by Spohn from 2014 and another one to 2015. I can give you references later. So what do we do in this mode coupling theory? We do the following. Well, first of all, let me just restrict myself to the strictly hyperbolic case when all the eigenvalues for current Jacobian are different. And this is something that is quite important, but one can also do it if this is not the case. Anyway, so if this is the case, then what happens is the following. The off-diagonal elements of this matrix, alpha, beta, and as well as the products, they decay quickly. The reason is, remember now what I said about these eigenmodes. They travel with a certain speed. Well, when you look at the fluctuations, then you basically look at an initial situation where you generate a peak somewhere, and then you see how it develops in time. But now different peaks move with different macroscopic velocities. So after a sufficiently long time, they will be so far from each other that they don't interact anymore. And therefore, these guys, you can be neglected. That means that of this whole function C alpha beta, only really the C alpha alpha will remain for long times and large scales. And then you end up with an evolution equation of this type here. Now, what you do to arrive at this diffusion, this equation are basically two things. Well, first of all, you take your nonlinear fluctuating dynamics equation and you construct a generator for it. And then you make the following assumption, namely that your fluctuation fields, these phi's, are basically Gaussian random vectors. And also you make some ad hoc assumption to close the equations. It's a very technical thing. I don't want to explain it in detail. I'm just telling you that there are two approximations involved that you cannot really control. So that means that this is an equation which might, in the worst case, be totally wrong. In the best case, it might actually be exact. It can be anything in between. And I will comment on this in a short while. But anyway, given this equation, you can try to analyze it. So you have here your linear part, and here is the part that comes from the interaction, which has these mode coupling elements inside, right? Which come from the nonlinear part of the current here, the G's. Okay, so as I say, here is what you have to assume. Well, first of all, just let me repeat, you have to discretize your coupled-Burgers equation, then you introduce a generator, and then you make these assumptions that you have this Gaussian random vector, which allows you to factorize multi-point correlations, which otherwise you could not treat. And then you make this closure approximation. And finally, you undo your discretization, but this is kind of harmless. The two non-tricky things are the fluctuation fields, this one here and this one. This is really the one that one should be able to prove somehow, but not aware of any proof of that. Anyway, the point is that this nonlinear integral equation, as untractable as it looks, is actually not untractable. Namely, it's a function of two variables, right? Of q and tau in real space of x and t. But now you can make a scaling ansatz. That is, you can look for solutions of the form q to the z times tau. And take q to 0 and tau to infinity. And then you find that you can actually, in this limit, you can actually solve these equations exactly. And you find that there are different kinds of solutions that depend on your mode coupling coefficients and the nonlinear terms that appear. Now, let me explain this here. Alpha is the mode at which you look at, alpha here, and beta, this is the mode to which there might or might not be a coupling in your coupled Burgers equation. So if for mode alpha, all couplings are 0, right? Then you just have the linear part, and then you find out, as you would guess, that you get dynamic exponent 2 for diffusion, and your structure function is thus the Gaussian, as for the symmetric exclusion, and as if there was no interaction at all for symmetric case. So you get diffusive scaling, the Edwards-Wilkinson, the universality class. On the other hand, if this mode alpha has a coupling to itself, then you are basically in the situation of the ASAP. You find that the dynamic exponent is 3/2, and this dynamic structure function, just this Brehofer scaling function, or perhaps some modification thereof that depends on the further detail I want to comment upon. But anyway, it is essentially the KPZ, or maybe some modified KPZ scaling. So far, it seems to be nothing new. However, there's a third situation, namely that the self-coupling vanishes, but that there are couplings to other modes, right? So this excludes this case and includes case 2 as well. Well, what then happens is something quite remarkable. Namely, these Z alphas cannot be arbitrary numbers, but they take specific values. And you can show that these values are the series starting 3/2, next being 5/3, 8/5, 13/8, up to 1 of square root of 5/2, which is nothing but the golden mean. And the S alphas, they're all Levy distributions, alpha stable distributions. So now if you look at these numbers, you realize that these are all ratios of neighboring Fibonacci numbers. That's why we call all these universality class Fibonacci universality classes, and these ratios we call Kepler ratios, because actually Johannes Kepler in a paper of 1614 first noticed the significance of these numbers in the shape of snowflakes. So now which of these guys occur, that depends on how many conservation laws you have. So for instance, if you have 3 conservation laws, you can have 3/2 and 5/3, but not be higher. And you can have the golden mean. If you have 4 conservation, if you have, hang on, no, wait a second. No, if you have 2 conservation laws, you can go up to 5/3 and have the golden leaf. If you have 3 conservation laws, you can go up to 8/5 and have the golden mean, and so on. So the more conservation laws you have, the higher you can go in the series, but you can always have this possibility of the golden mean if you have at least 2 conserved laws. Okay, so that's the picture here. Just as I say, this mode coupling theory, which gives the result as many uncontrolled approximations, so you might worry about whether this is true or how good it is. So we made some simulations on the exclusion process with 3 lanes. This is an old paper from 2015, where according to the mode coupling theory, one of the modes should be an 8/4 Levy, another one 5/3 Levy, and the third mode 3/2 KPZ. Now, here's just one picture, but this is representative for all of them, of this 8/5 mode. So here you see the evolution of the 3 modes, right? At time 0, you have 3 distinct peaks, but not 0, close to 0, right? And then they start to move away from each other and they broaden in time, right? And it's this broadening that's described by the scaling function. And the mean velocity is the eigenvalues of your current jet. Okay, so now look at time 1000, right? Should be somewhere here in this picture along this line, the cut through here for the 8/5 mode. Here you see a picture that shows you two things, even though you see only one. Namely, it shows you the theoretical prediction of the mode coupling theory, and it shows you the simulation data. The reason why you see only one is because they actually collapse totally on top of each other. Here we have made zoomed in a little bit. Here in the central part, you see the black curve. This is the 8/5 Levy distribution, and the red dots, they are the simulation data. They follow the curve exactly. But you can see this happens not only in the central part, but also in the tails of the distribution, right? The increment is quite amazing. That means that even though this mode coupling theory has many uncounted approximations, it's actually almost exact. Okay, now, so again, let me just recall why perhaps this theory is so good. It's just one example. There are many other examples where it's equally good. Namely, first of all, this coarse-grained evolution equation, namely this nonlinear fluctuating dynamics equation, is fully determined by only three macroscopic quantities, namely the diffusion constants, which you have to put in by hand, the stationary currents, which you can compute from the invariant measure, and the static composability, which also comes from the invariant measure. So from macroscopic quantities already determines the form of the equation. And then the assumptions that kind of go into the argument that this is a kind of universal tool really are that you have short-range interactions and local conservation laws. And so this is really the most important point. So that really, when you look at the relaxation, the only thing that's relevant at large times are the slow variables, which are the conserved quantities, right? And now if you look at very large waves, then of course microscopic details gets washed out. This is the philosophy behind believing that this is universal. That's why we believe it can apply to these many different systems. But again, so that it works somehow is perhaps not so surprising because of these things. But why is it so good? When does it break down? And are there perhaps any rigorous results where we can prove something, right? So this is one set of questions. I will not address them today. But there's another question. This computation has been done only for strong bias. What happens if the bias is weak? And what can we say about crossover behavior between different universality classes? This does not come when you look at strong bias. And it's this question here that I want to look at. Okay, so how do I do this? And this is really the main part of my talk. And I will do this only for the ASAP in its weakly asymmetric form. So let me just recap. We need the static compressibility, which is from the invariant measure. You get just is equal to rho times minus rho. Need the stationary current. Speed times rho times minus rho will be the difference of jump rates. And we need the current Jacobian, which is the derivative of the collective velocity. It's speed times minus 2 rho. And we need this mode coupling term, which is the second derivative, the Hessian, so to speak, just a number, which is the second derivative. So these are the quantities that we need. And then we have to add this diffusion coefficient in a phenomenological way. But anyway, so this is the exclusion process. Now I look in the thermodynamic limit, and these changes, of course, these quantities don't change. They don't depend on that. And now look at the following regimes. First of all, this bias, the difference of rates, in one case, I just take to be a constant. That's the ASAP. In another case, I take it to be b times epsilon to the power kappa, where epsilon is a parameter that will take small in a way that they will specify, and then I call it WASAP, weakly asymmetric exclusion process. And of course, if there's b, this small b is equal to 0, then it's just a symmetric case, right? Okay, so now again, let me recall what we know. If we do the hydrodynamic limit under diffusive scaling, so if we rescale microscopic time by a factor a squared, if we remove space by a factor of a, then the hydrodynamic limit will be the diffusion equation with this diffusion coefficient. If we have a strong bias, that is, if kappa is equal to 0, just some constant, then we do Eulerian scaling and we get the implicit Burgers equation, which is a kind of Kardar-Parisi-Zhang equation without viscosity. Okay, so that's about the hydrodynamics. Then we do the nonlinear fluctuating dynamics. That is, we take the first order expansion, the second order expansion of the previous equations, and we add diffusion and noise, right? Then what we get is this guy here, this equation. This is nothing but a noisy KPZ equation if we take phi equal to b dxh, right? Otherwise, noisy Burgers equation. Now, the mode coupling theory that I've described before will give us this integral equation that I've shown you. And now we make, in that integral equation, make a scaling ansatz. We take the Fourier transform, we take the momentum to 0, take t to infinity, such that p to the power z times t is fixed for some z. Now it turns out if we take z equal to 2, then we will get an exact solution of this mode coupling equation for g equal to 0, which means that b is equal to 0, so for symmetric exclusion. So this we know, this is actually an exact result. So in this case, this mode coupling in a trivial way reproduces an exact result. And if we take the ASAP, the strongly asymmetric case, and we take 3/2 as dynamic exponent, then the solution of the mode coupling equation will be some non-trivial function which is given by an integral equation which has been solved numerically and turns out to be not so different from this exact Brehover-Scone scaling function. So this is consistent with the KPZ universality, but the mode coupling theory gives the right exponent, 3/2, and the scaling function which is not exactly the correct one, but something which is at least numerically close. Okay, so that's the known thing for strong asymmetry or for the symmetric case. Now what happens for the weakly asymmetric case? So again, what do I mean by weakly asymmetric? It means that I take the scale at which I rescale my lattice to be equal to the epsilon, which is the parameter that appears in the weakness. So basically, I take the weakness to be proportional to the scale, the lattice scale, the kind of lattice unit to the power kappa. In Fourier variables, it means that I take the microscopic momentum be equal to epsilon times p, with p fixed and epsilon to 0, and microscopic time tau, I take to infinity as epsilon to the minus chi times t, where chi defines my speeding up of time, which I now keep as a variable. And so I allow it to be any value that I wish. Okay, now this case has been treated mathematically rigorously for chi equal to 2. What turns out is that if this kappa in the weakness is larger than a half, then you get Edwards-Wilkinson universality. It means you get diffusion, essentially, the diffusive correlation function for any kappa, if as long as larger than 1/2. So this is already a non-trivial result because it's not exactly equal to 0, the asymmetry, but it's somewhat small. Now, if kappa is equal to 1/2, then something else happens. The fluctuation fields, properly defined, they satisfy, well, in a weak sense, noisy Burger equations. So for kappa equal to 1/2. Now, what happens for kappa less than 1/2, but not 0? Well, this, as far as I know, there's no result on this one, but it has been conjectured, and there's one paper where this has been mentioned, that you get KPZ universality if you choose kappa to be equal to chi minus 3/2, or conversely, if you choose your observation scale equal to kappa plus 3/2. Okay, so this is a conjecture. Another remark I would like to make, if you take kappa equal to 1/2, you get this noisy Burgers equation. But then in this paper by Castell and Sarkar, they point out that this noisy Burgers equation is actually as such not scale invariant. But if you look at the large scale solutions, large scale behavior, then it flows to this KPZ fixed point. That's what they say there, right? So this is something to be kept in mind here. So here we expect universal behavior in the Edwards universality class. In this range, we expect universal behavior in this KPZ universality class. And at this one here, it's a bit unclear what exactly to expect. So let's treat this now with this mode coupling theory, this problem. But not with the mode coupling theory that I've done before, because the way how it is phrased, you really can treat only kappa equal to 0. And also, you cannot really get a crossover behavior. So the approach that I choose is a different one. First of all, I make no assumption of scaling to solve this equation, right? I just take it as a function of two variables without assuming that it's a function of only p to the power z times t, right? So this is the first thing. So I do not put scaling assumption into the equation. And moreover, I look at two distinct large scales. So basically, I have two video cameras on top of each other. First, I zoom in or zoom out in the way I have described before. So I take this limit epsilon to 0 with q epsilon p and tau epsilon minus chi tau t with this observation exponent chi as a variable, right? This will define what I will call mesoscopic scale. So now I will get something which is a function of p and t, right? Because this is the way I've chosen if I take this limit, and of course it will also depend on chi and kappa. Now, given p and t fixed, I take the second camera and take also p and t, p small and t large. That is, I rescale p with some small parameter delta times tilde p, and tau I take large to be large with delta to minus chi tilde times t tilde. So it's another video camera. So I watch my first video camera with another video camera, right? And I zoom out and I speed it up with this exponent chi tilde, and I see what I observe then. Clearly, if what I see here is scale invariant, I will see the same here because I just changed scale, right? So it will not make any difference. But if what I see here on this scale is not scale invariant, then what I see here on that macroscopic scale will be something different. So we want to see what. Okay, now to implement these ideas, we have to use some technical ingredients. Now, the way how I do it is, first of all, I discretize my nonlinear fluctuating dynamics equation with microscopic coordinates k and tau. This is a kind of simple technical device, should not be very difficult. So basically what I will end up with a discrete stochastic Burgers equation, which then I kind of expect to have the same universal behavior as the exclusion process, because this is the general idea behind this nonlinear fluctuating dynamics approach. Then I will do this mode coupling approximation, as explained before, which gives me a discrete mode coupling equation. I take the Fourier transform, so I go from space to my Fourier variables, and then introduce my observation scale that I've just mentioned before, right? So I take Q small, tau large with p and t fixed. Okay, so this will just be the same that I've done before. The new step comes now, namely, instead of studying my structure function as a function of p and t, I study it as a function of two different variables, zeta I. And I choose them to be equal to epsilon to some power, which I parameterize in this way, times ui, and ui is a scaling variable I've defined here, which depends on p and t. And here there are parameters, chi, zi, li, which at this point can be anything. They can depend on all these parameters of my exclusion process, which means the b, the kappa, the d, the density, and whatnot, right? All the parameters that are in the model can enter into these parameters here, right? This is just an ansatz at a start. Now, you put this into your mode coupling equation, and then if you look at it long enough, you will realize that if you choose your scale parameter L1 to be square root of 2 times g, where the small g is just the big G times epsilon to the power kappa, so this is a constant, you choose L2 equal to D, and if you choose as this parameter Z1 and as Z2, the values 3 over 2 and 2, respectively, just constant, irrespective of model parameters, then you will realize that the mode coupling equation that I've written down before will not depend in any form anymore on these G's and D's. They will depend only on epsilon in an explicit form and on chi and kappa. So, right, so the only dependence will be here. This will be absorbed into your arguments of your new function. And that simplifies a lot, because now you can actually take the limit where epsilon goes to 0, and you end up with the following. This is the main result. So you end up with an mode coupling equation, which is an integral equation, which has no parameters anymore at all. And okay, so imagine I found a solution of that equation, right? I have no explicit form of that solution, but it's an equation that you can solve numerically, or maybe one can even come up with an explicit solution, which I don't know how to do, but anyway, maybe it's possible. Point is that if you have this function, then you can show that this limiting dynamic structure function, that is the microscopic structure function in this limit epsilon to 0, is equal to the following. I define this critical observation scale, which is 3 over 2 plus kappa or 2, depending on which of the two is smaller, right? So if chi is less than this chi star, then this function is just equal to 1 independently of p and t, right? Now, if chi is equal to this value, it is something different. Now it depends. If kappa is larger than half, then you see that the min is just 2, right? And then it's a function of only the second scaling variable, u2. And now let me just go back. u2 is p times d times t times 1 over 2. So here the dynamic exponent is equal to 2. Okay. Oops, sorry, this way. Now, if chi is larger than chi star, if kappa is less or equal to is less than a half, then it's a scaling function only, is a function only of u1. u1 is this p times the square root of g times t to the power 2 over 3. Now, if kappa is equal to half, it's a function of both scaling variables, which this is the result. So just repeat, we have a function sigma, which is a solution of an integral equation which has no parameters at all, right? Just some integral equation that you get as a limit of the mode coupling equation. For chi less than chi 0, the dynamic structure function is 1. For chi larger than chi star, it's 0. And otherwise, it is a function of the second variable, scaling variable only, or a function of the first scaling variable only, or if kappa is equal to 1/2, a function of both variables. Okay, so this is what comes out. Okay, what does that mean? Well, first of all, it means that we have a non-trivial scale invariance for chi equal to chi star. Non-trivial in the sense that, of course, if s is just equal to 1, is all scale invariant, but of course it's trivial. It doesn't mean a great deal, and the same for 0, but it's a non-trivial one for at this critical value. But at this crossover point, 1/2, it depends on both scaling variables, and they scale in a different way under rescaling. So there is no scale invariance at this particular value. Now, for kappa less than 1/2, you get the superfusive KPZ dynamic exponent 3 over 2. And the scaling function, you will see that this integral equation for kappa actually reduces to the integral equation that was already looked at in 1985 in this old paper von Bayern. So that means that the scaling function in the mode coupling approximation is independent of kappa as long as kappa is less than 1/2. And this is indeed strong support for the conjecture that these variable fluctuations are governed by the KPZ fixed in the whole range kappa less than 1/2, not only at kappa equal to 0. Now, if kappa is larger than 1/2, then the mode coupling theory tells you that we get the Edwards-Wilkinson universality class, and you can actually, in this case, solve this equation exactly. We just get the Gaussian, right? So it reproduces an exact result. And at the crossover point 1/2, this absence of scale variance is, I think it's just a mirror. Just comes from the fact that you have this lack of scale invariance in the stochastic Burgers equation. I think this is really related to it. I mean, of course, it cannot be shown explicitly, but this seems to be the underlying reason for that. Okay, so that means just to look at this picture here. Here is kappa, right? Here's my observation scale chi, which I can choose as I wish. If I'm in this region, so I take kappa larger than 0, but chi less than 2, then my structure function is just equal to 1. Now, what does that mean, equal to 1? Well, it means that there is no spreading. It's just a peak that moves. So you scale in such a way that you do not see this spreading of the peak. You just see the way how the peak moves. And this way, the structure function is equal to 1. On the other hand, in this regime here, when chi is too large, the structure function is equal to 0. That means there are no correlations anymore. That means they're just completely uncorrelated. The system has relaxed, and there are no correlations between these two fluctuations anymore. But here on this line, you get interesting behavior. Here you get the Edwards-Wilkinson universality class for kappa larger than 1/2 and chi equal to 2. Here for 3 over 2 plus kappa, you get KPZ universality. And here at this point, it's not scale invariant, which is governed by the stochastic Burgers equation. Okay, so that's what I want to say about this mesoscopic limit. Now let's go to this macroscopic limit. So remember, so far I have a function of the scaling variables ui, which are functions of p over t to the power 1 over zi. Now I take p to 0 and t to infinity again. So I look at this second limit. In this fashion here, I take p equal delta to tilde p with delta p constant, and I take t equal to delta minus chi tilde times t tilde, where t tilde is a constant. And if you just plug this into this result that I've shown you before, then you see that you get a non-trivial scale invariance only when chi is equal to chi star. That is, if your first video camera is zoomed out in such a way that you are on the critical line. Then you can see non-trivial scale invariance also on macroscopic scale. But what you see, that depends. If you choose now your macroscopic observation scale to be equal to 3/2, then what you see is the following. My macroscopic structure function is just a normalization factor, can forget it, is equal to 1 for kappa larger than 1/2. It's equal to a function of the first scaling variable for kappa equal to 1/2, and it's equal to the same function. It's the same function for kappa less than 1/2. Now, what that means is the following. It means that even at kappa equal to 1/2, you see KPZ scaling, right? Remember, this was the scaling that characterized the KPZ universality class. So that means in the whole range from 0 to 1/2 inclusive, you get KPZ-like behavior. So this really means that this crossover point, kappa equal to 1/2, is scale invariant also on macroscopic scales. Not scale invariant on mesoscopic scale, but it's scale invariant on macroscopic scale. So that means there is no, of course, if you look at values less than kappa, it's the same because it was already scale invariant before, right? So remember, at kappa equal to 1/2, this was a function of u1 and u2. You scale it again, and then this second variable is just scaled to 0 in this limit, right? And that's why it becomes a function of 1 only. And here, if you look at 2 strong kappa, but on this scale, you just see the peak moving on that scale. Okay. Now, of course, you can take another macroscopic limit. You can take this chi tilde equal to 2. In that case, what happens is that for kappa larger than 1/2, you see the same as before, as you would expect, because this was scale invariant already. And so if you do another scaling, the result will be the same. Now at kappa equal to 1/2, it's 0, and also kappa less than 1/2. So this is completely consistent with what we had before. It should be so. It should be 0 because we know that you get non-trivial scaling behavior for 3/2 and not for 2. So that means on macroscopic scale, our phase diagram looks a bit different. Here's kappa, here's the in tilde chi. For kappa less than 1/2, you see KPC behavior for 3/2, including the value of 1/2, and Edwards-Wilkinson behavior for kappa larger than 1/2. And if chi tilde is too small, you see ballistic behavior. If chi tilde is too large, you see relaxation. So that's the story in these 2 limits. Okay, and that brings me to the end of my story. So the main results, as I see it, is that, first of all, this mesoscale mode coupling theory is consistent with all mathematically rigorous results that we know. And it is also in reasonable agreement with numerical results. I mean, the numerical result is in reasonable agreement with the exact Breuer-Schwann function, even though we have all these uncontrolled approximations. So the uncontrolled approximations do not seem to be so bad. Now, at the crossover point, kappa equal to 1/2, we have a non-scale invariant crossover behavior on mesoscopic scale, such that you get, for kappa less than 1/2, the KPZ fixed point, for values less than 1/2, and for values including 1/2 on macroscopic scale. And this scaling function, this is just the integral equation it's the same integral equation which has no free parameters, just a function that's given by parameter-free equation. Okay, so this is the approach that can be extended now to many conservation laws, but this hasn't been done yet. So this, I think, would be interesting to do. So we take the same approach to many conservation laws when we get these Fibonacci universality classes for strong bias. So the question is, will we still get the same? I would imagine yes. But then there will be the question of crossover points and at which observation scales we actually see these guys, right? This is it's not only which exponents do we find, but also how do we have to zoom in to see it, right? This is what also this mesoscale theory tells you. And this, I think, we will also be able to find out here. This will certainly be useful for mathematical proofs because then you know already how you have to rescale space and time in order to get the result that you want to prove, which otherwise a priori is not clear. Then there is this still this open question why these theoretical scaling function simulation data are so agree so well. Well, there's one example that was studied by Patricia and by Cedric in 2014, where we can actually prove exactly the equation which the structure function should satisfy. And this, if you look at the solution, you will see that the mode coupling theory is actually exactly the same, including all the coefficients. So for one example, the mode coupling theory is actually exact. This doesn't mean that it's generally exact, but at least there is hope that we can understand what precisely is going on, and maybe one can even prove at least some of the arguments that enter this mode coupling theory. Okay, so these, I think, are the questions that are interesting from a mathematical perspective. Of course, there are other interesting questions, but it's just what I want to mention now. And thank you for your attention.
Thank you very much, Gunter. Yeah. Are there any questions or comments? Let's see. So I was wondering, so you said that there are some exact results about this mode coupling. Is there I mean, do you expect that for other models the results would still hold but are not exact because of I don't know, the models are less special?
Yeah, that's really something that we're trying to understand right now. I mean, we're actually working right now on the two-line exclusion, at least for this case where you get a diffusive mode and the 302 Levy mode. There are still some technical difficulties we have to solve, so we don't know yet what the result will be. But I'm quite optimistic that we will get this Levy scaling function that looks like it. Whether the coefficient that comes in this scaling function is the one that mode coupling theory predicts, this is another story. I don't know yet, but it's certainly a question that one can try to understand. But it's not easy to make these proofs because one has to estimate certain higher order correlation functions, which is not an easy thing to do. If you take all these limits.
Let's see if there are more questions. I just have a comment, like so can I say that, I mean, the way to interpret this mesoscale regime is the right one to look that show that the crossover is the K1 alpha is not lost, because then if I go to macroscopic, I don't see anything special about this, I don't know, phase transition in K1 alpha. Is it correct to interpret these two different regimes?
Well, look, it seems to me that at these crossover points, the noise that you have in your description is so strong that you cannot ignore it. But as soon as you zoom out on this level, the noise kind of becomes smaller and smaller, and you end up with that kind of stochastic behavior that would characterize these other universality classes, which would be KPZ or whatever. But as I said, we don't really know yet what happens in the Levy cases, what the crossover there looks like in these cases. It's not clear to me at all. It could very well be that then you get crossover between, let's say, diffusion and 3/2 Levy. So you would have a macroscopic equation that has a Laplacian and a fraction Laplacian at the same time, which is almost scale invariant. So this is one possible scenario that what the mesoscopic equation would look like.
I see. Okay, let me just check if there is something online. No, I don't think so. So thank you very much, Gunter, for the presentation.
Thank you.
And we update next Wednesday, same time, same place.
Okay.
Bye-bye, everyone. Bye, Gunter.
Bye.
Thanks
Bye,
again.
everyone. Thanks, Gunter.
Bye, Clement.
Bye.